Throughout this unit, we have examined how the ocean moves through waves, tides, surface currents, and even deep circulation. But most people experience the ocean at the shoreline. The coast is where ocean energy becomes visible and tangible. Shorelines are not fixed boundaries between land and sea. They are dynamic systems shaped by the interaction of wave energy, tidal range, and of course, sediment transport. Today, we will examine how waves transform as they approach shore, how sediment moves along the coast, and why shorelines constantly adjust to changing conditions. Several slides in today's lecture will add material to topics already covered. Some of this will sound like a review, but we're going to go a little deeper. When waves travel across deep water, their motion does not interact with the sea floor if the depth is greater than half their wave length. But as waves approach shore, water depth, of course, decreases. When the depth becomes less than half the wavelength, orbital motion begins to interact with the sea floor. We've talked about that before. Friction between the moving water and the bottom is going to slow the wave. Wave speed in shallow water depends on depth. As depth decreases, wave speed decreases. However, as we have discussed, wave period does not change. The time between crests remains constant. So if speed decreases while the period stays constant, then the wave length must also decrease. So now consider energy conservation. Energy contained in a wave is generally conserved as it moves toward the shore. If wavelength shortens while energy remains similar, then the wave height must also increase. This process, as you know, is called shoaling. Shoaling explains why waves grow taller as they approach the shore. This slide works to review the important sequence. As depth decreases, wave speed decreases, wave length shortens, and wave height increases. This is the first transformation that allows wave energy to affect the coastline. Waves rarely approach the shore over uniform depth. The seafloor is irregular. Some areas are going to be shallower than other areas. Because wave speed depends on depth, the part of a wave entering shallow water first slows down first. The rest of the wave continues moving faster in deeper water. This difference in speed causes the wave crest to bend. This bending is called wave refraction. Wave refraction redistributes energy along the coastline. Headlands, which extend into deeper water, causes waves to slow first at their tips. Energy becomes concentrated there, as you can see in this illustration. Bays, being shallower and recessed, receive less direct wave energy because wave fronts bend around them. Over time, refraction tends to erode headlands and deposit sediments into bays, which, on a broader scale, serves to smooth the irregular coastline. So wave refraction explains why shorelines evolve toward more uniform shapes. As shoaling continues, wave height increases and wavelength decreases, wave steepness increases. When steepness reaches a critical threshold, the crest becomes unstable. The crest moves faster than the base because orbital motion near the surface is less affected by bottom friction. Eventually, the crest outruns the base and collapses forward. The wave breaks. Breaking converts organized wave motion into turbulence. This turbulence transfers energy to the shoreline and to sediment particles. Breaking waves are therefore the primary mechanism delivering energy to the coast. I include this slide in today's lecture as a reminder that erosion and sediment transport are not caused by water motion offshore, but instead by breaking waves in shallow water. When waves approach the shoreline at an angle rather than straight on, the physics of sediment movement changes. The breaking wave pushes water up the beach face. This uprush is called swash. Because the wave approached at an angle, the swash also moves diagonally up the beach. After the swash loses momentum, gravity pulls the water back downslope. This return flow is called backwash, and it generally moves straight down the steepest slope, perpendicular to the shoreline. You can see the swash and backwash labeled in the image on the left. So sediment grains are pushed diagonally up the beach and then pulled straight back downward. This results in a zigzag path. Over many waves, that zigzag motion produces a net movement of sediment parallel to the shoreline. This is called longshore transport, and the moving water responsible is the longshore current. Now connect this to what we know about waves and even about tides. Wave refraction controls where waves approach at angles. Wave energy determines how much sediment can be mobilized, and then tidal elevation determines how far up the beach the swash is going to travel. Longshore transport is therefore not an isolated process. It is the direct mechanical consequence of angled wave breaking combined with gravity acting on the backwash. Over months to years, this process can move enormous quantities of sand along a coastline. So a beach is not permanent. It exists only as long as sediment supply balances sediment removal. Sediment enters coastal systems primarily from rivers and from erosion of cliffs and headlands. Rivers deliver sand, silt, and clay to the coast. Coastal erosion supplies additional material. Once sediment reaches the shoreline, longshore transport redistributes it. Some areas experience net gain, where sand accumulates and the beach widens. Other areas experience net loss, where transport exceeds supply and erosion dominates. This creates sediment sources and sediment sinks. For example, If a river supplies large amounts of sediment, beaches downdrift of the river may widen. But if sediment supply is cut off by, say, damming the river, for example, beaches may narrow and begin to erode. So activities that are done on the river, even far from the shore, may have significant impact to the beaches. Students, you should understand that shoreline position reflects a dynamic balance. Sediment input minus sediment output equals shoreline change. Wave energy determines transport capacity. Sediment supply determines whether erosion or deposition occurs. Beaches are therefore sediment storage systems controlled by ocean energy. Tides do not generate waves, but they strongly influence where wave energy is applied. Consider a coastline with a small tidal range. Wave energy is concentrated within a narrow vertical band. Sediment movement and erosion occur within that limited zone. Now consider a coastline with a large tidal range. Waves interact with a much broader vertical region of the shore, the zone of active sediment transport it spans. Tides also influence the slope of beaches. On coasts with large tidal ranges, beaches tend to be wider and flatter because wave action is distributed over a large vertical area. The photograph on the left shows a beach along the Georgia coastline. The shape of the coastline in the eastern United States creates a V or a U-shaped coast with Georgia right in the middle. The tidal range in Georgia, therefore, can be more than 3 meters. The photograph on the right shows a beach at a high tide and at a low tide. A 3-meter vertical tide equates to more than 50 meters of horizontal space on the beach because their beaches are so flat. So that is a lot of space for sediment to be picked up and transported. Additionally, tidal currents in estuaries can transport sediment in and out with each cycle, influencing deposition patterns. So while waves deliver energy, tides modulate where and when that energy acts. Erosion occurs when the energy delivered by waves exceeds the resistance of shoreline material. In sandy environments, erosion means sand is transported offshore or alongshore faster than it is replaced. In rocky environments, repeated wave impact exerts hydraulic pressure in cracks and fractures. Over time, this undercuts the cliffs and can lead to collapse and retreat. You can see 2 examples of that happening in the images on the slide. Storm waves are especially important. During storms, wave height and period increase. Longer period waves carry more energy and penetrate deeper into shallow water before breaking. Storm surge can also elevate water levels, allowing waves to reach portions of the shoreline that would normally be out of reach. Erosion is therefore not constant. It is episodic and energy-driven. The key here is to understand that erosion reflects imbalance between wave energy and material resistance. Barrier islands are long, narrow accumulations of sand parallel to the mainland coast. They form in regions where sediment supply is high and wave energy redistributes sand offshore and alongshore. Barrier islands are not fit structures. During storms, waves can overtop the island, carrying sand from oceanside to the back barrier lagoon. This process is called overwash and is routinely seen when hurricanes pass through. Over time, overwash causes barrier islands to migrate landward. Barrier islands therefore respond dynamically to sea level change and storm frequency. They are maintained by continuous sediment transport and, of course, reshaping. Let's once again take a look at the Georgia coastline for an example. Georgia's islands are a composite system formed by two distinct generations of sand deposits separated by thousands of years. While modern barrier islands typically move landward with rising seas, a new chain of Holocene islands, formed about 5,000 years ago, developed seaward of the older Pleistocene islands that formed over 40,000 years ago. The older islands are shaded in purple, and you can see they are closer to the mainland than the younger islands shaded in yellow. Over time, these younger islands migrate toward the shore, and some have even welded or connected into the older ones, creating the unique double-ridged landscape we see on the maps today. These younger islands will continue to migrate based on the influence of tides, storms, waves, and currents that continuously and constantly reshuffle the sand on these beaches. The image on the left of this slide is from a famous beach on the northern tip of Jekyll Island. Locals call it Boneyard Beach. The beach is eroding on the north end of the island due to a constant flux of waves angled from the north. As the sand is carried down the longshore current to the south end of the island, erosion has penetrated the maritime forest, which was once protected by a large dune system. The dead trees you see in this image did not wash up on the beach. They were once alive and thriving right there in position. That beach you see today used to be a thick maritime forest with oak trees. Human structures often interfere with natural shoreline processes. A jetty built to stabilize an inlet interrupts longshore transport. Sand accumulates on the updrift side, while beaches downdrift may erode due to sediment starvation. The image on the left side shows what happens when a rock jetty is built. The bottom two images show how the jetty will trap sand and allow the sand to accumulate on the upstream side of the jetty. This is good for those properties because it adds more beach. However, the downstream side of the jetty is a different story. Look closely in the top two images and you'll see the jetty off in the distance near the horizon. Downstream of the jetty, the sand still erodes off the beach, but there is no sand coming from the longshore current since the jetty now is blocking sediment transport. So the beach there erodes with any additional input of sand. This causes the beach to erode inland and puts the beachfront property at risk. The top right image shows a significant loss of beach and property only 25 years after the jetty is built, including the loss of buildings and other forms of development. Seawalls reflect wave energy rather than dissipate it. This can increase erosion at the base of the structure and lead to the seawall to collapse. Beach renourishment attempts to restore sediment balance by adding sand artificially, but without addressing underlying transport dynamics. So erosion continues. Many of our current engineered solutions do not account for wave energy and sediment transport mechanisms. All we're doing is relocating sand after erosion and placing back in the same spots where it will erode again. The United States spends more than $300 million each year on shoreline restoration. Florida alone spends over $50 million each year for just renourishment projects, where sand is put back on top of eroding beaches, without any interest or effort to maintain sediment transport. All of that sand is going to simply erode back to the sea once again. It is a terrible cycle that we created to protect homes, hotels, and other development along the shoreline. The physical properties we have discussed throughout today's lecture and this entire unit influence the habitat along the coastline. Rocky shores, sandy beaches, tidal flats, and barrier islands exist because of the energy regimes that shape them. In the next lecture, we move from physics to ecology. We will examine how organisms adapt to the physical forces we've described, and how habitat structure reflects underlying ocean dynamics. The biology of the coast is built on the physics of the coast.